Okay, for this next one, we're going to use an equation. You, of course, will be provided the equation and the constant that I'm going to use in this equation. But it ends up for the hydrogen atom, not for a whole lot of other atoms, but for the hydrogen atom, there's a really simple relationship between the energy of transitioning between the different states of the atom. And so delta E, the change in energy between the two states, is equal to a minus, and we cannot forget the minus, a constant called Rydberg's constant times 1 over NF squared. This is going to be the final state minus 1 over Ni squared. That's going to be the initial state. There's several ways of writing this equation, but I think this is the best one, and this is the one I'll provide for you. So what does all this final and initial business mean? So from and to. So we started in the n equals 2 state. So that is the initial state, and we go to the n equals 1 state. So let's put our numbers in, and I'll put the Rydberg constant in last. Since it's a huge number, we'll add it after we've kind of done this part in the middle here. So let's do 1 over, so the final state is 1 over 1 squared, minus 1 over 2 squared. The part that's there in parentheses. So this is equal to 1 minus 1/4, or 3/4. Part in parentheses is. And so now delta E is equal to, and I can't lose my minus, minus 3/4 times the Rydberg constant. And now I'll put the Rydberg constant in for you. So the Rydberg constant is equal to 2.187 times 10, I have to look, 10 to the minus 18 joules. Okay, so then my energy for this transition is minus 3/4 times this big number, or small number actually, 2.187 times 10 to the minus 18 joules. Three-fourths times 2.187 times 10 to the minus 18. Okay, so this energy, the energy of this transition is, okay, don't lose my minus, minus 1.64 times 10 to the minus 18 joules. Okay, and the reason that this is negative is we've taken a high energy state, n equals 2 state for hydrogen is a high energy state, and we've allowed it to relax down to its normal, comfortable ground state. And so going from a higher energy state to a lower energy state releases energy. That's how we get that negative. Well, let's start that electron in an even higher energy state. Instead of n equals 2, it's in an n equals 3 state now. So delta E is equal to minus the Rydberg constant times 1 over, oh, do that again. My final state is the n equals 1, so 1 over 1 squared minus 1 over 3 squared, which is equal to, this inside part is equal to now minus RH. So 1 minus 1/9 is 1 minus 1/9 is 8/9. Okay, 1 is 9/9, and 9/9 minus 1/9 is 8/9. Okay, so now our change in energy here is minus 8 over 9 times that Rydberg constant again, 2.187 times 10 to the minus 18th joules. Okay, equals 1.94 times 10 to the minus 18 joules. All right, well, this final one is familiar-ish. So we started here with an excited state and allowed it to relax to its stable ground state. We started with an even higher excited state and allowed it to relax to its stable ground state. Here, we're going to have to put in energy. We're going to start it at the ground state and excite it to the excited state. But a lot of this should look familiar. So delta E is equal to minus Rydberg's constant times, so my final state here is the n equals 2 state, so 1 over 2 squared minus 1 over 1 squared. So what are we getting here then? So minus RH times 1/4 minus 1. Okay, that's minus 3/4. Up here at the top, when we were looking at the other one, it was plus 3/4, and then the plus 3/4 got multiplied by the minus sign here and became minus 3/4. But now a minus times a minus is going to make our change in energy a plus. Minus times minus gives me a plus, so plus 3/4 times the Rydberg constant. And of course, it's going to end up being this same number, just with a positive sign now. So plus 1.64 times 10 to the minus 18 joules. Okay, the only difference being, for this first one, we released energy. For this second one, to cause the stable atom to go into its excited state, we have to put in energy. This would either be heating it very, very hot, or hitting it with exactly the correct frequency of light to cause the electron to jump from its stable orbit into an unstable n equals 2 orbit.